Hi, everybody. Okay, so yeah, we're grading the midterm and we'll have that back to you by Monday, and I'll post solutions later today. So today is it's essentially the last lecture on linear algebra. Maybe we'll do a little bit more next time, but the last full lecture on linear algebra. And what we're going to do today and a little bit of the next lecture is chapter 7. And you know, at a very high level, chapter 7 combines the concepts from chapter 5, which was about eigenvalues and eigenvectors and diagonalization, with the concept from chapter 6, which is about orthogonality, to get some very, very useful results, which are possibly the most generally useful results in the course. So we're going to do 3 things today. So we're going to talk about the spectral theorem, which is the content of section 7.1. Then I'm going to define singular vectors, which are okay. They're not the same as eigenvectors, but they're you know, in some ways they're sort of like eigenvectors, but they can be defined for rectangular matrices. And then finally, I'm going to start talking about the singular value decomposition. And I'll finish that next time. So, you know, to put this in context, so what have we been doing so far? Well, in chapter 5, what we did is that if you have a square matrix, an n by n square matrix, then, you know, by chapter 5, you can diagonalize it sometimes. So you can find a diagonal matrix D such that A is similar to D. And we saw that this is useful for a number of things, but this has a few shortcomings. The first one is you can't diagonalize every matrix, right? As we saw, only some matrices are diagonalizable. The second shortcoming, which is a little bit annoying, is that sometimes you need complex eigenvalues. And the third shortcoming, which is really basic, is that this doesn't even make sense for rectangular matrices, right? So what we will do now is we will observe that there's a large class of matrices for which these things don't happen. So really what we'll show is that the first 2 things, this is not an issue for symmetric matrices. And the third thing is the singular value decomposition, which will be some kind of, you know, version of diagonalization for rectangular matrices. So the focus first will be on symmetric matrices. So let me define what a symmetric matrix is. So an n by n real matrix, symmetric if A is equal to its own transpose. Okay, so in terms of entries, that means the ij entry is equal to the ji entry. Okay, so we're going to focus on these matrices for the first half of the lecture. And, you know, as an example, if you look at this matrix, I guess I'm using square brackets. If you look at this matrix, this is symmetric. But if you look at, let's say, this matrix, this is not symmetric, right? Because it's not, if you take the transpose, it changes. So that's the definition of a symmetric matrix. And symmetric matrices are really important. In fact, in physics, for example, almost all matrices that show up are symmetric. And we're going to see that they have a bunch of special properties. Okay, so the special property we're going to be interested in is called orthogonal diagonalizability. So let me define that on the next slide. So a matrix, a square matrix A is orthogonally diagonalizable if there is an orthonormal basis of Rn. So that means n unit vectors that are orthogonal consisting of eigenvectors of A. Okay, so that means that these satisfy the eigenvector equation. Okay, so this is stronger than being diagonalizable, right? So diagonalizable means that there's a basis of Rn consisting of eigenvectors of A. Orthogonally diagonalizable means that there is an orthonormal basis. So this is stronger than being diagonalizable. Okay. And in terms of matrix algebra, this is you can write this in a different form. Equivalently, A is equal to PDP inverse, where P, remember, P is the matrix of eigenvectors, right? For a diagonalizable matrix is an orthogonal matrix. And okay, and what do you know about the inverse of an orthogonal matrix? So remember, an orthogonal matrix is a matrix whose columns are orthonormal. What can you tell me about the inverse of an orthogonal matrix?
Would it be that the rows of the inverse are also an orthonormal basis?
That's true. The rows are also an orthonormal basis. But suppose I gave you an orthogonal matrix and asked you to compute its inverse. What would you do?
It's its transpose.
It's just its transpose, right? Because orthogonal matrix means P transpose equals P transpose P equals identity. So orthogonally diagonalizable means A is equal to PDP transpose for an orthogonal matrix. So this is the property we're going to be interested in. This is a stronger property than diagonalizability, right? So this is stronger than diagonalizable. Okay, so one sort of easy observation is that if a matrix is orthogonally diagonalizable, then it must be symmetric. If A is orthogonally diagonalizable, then, okay, maybe I'll move this over. Then A equals A transpose. Okay, so being orthogonally diagonalizable implies symmetry. So this is an easy fact. So what's the proof of the easy fact? Well, it's just matrix algebra, right? So if A is equal to PDP transpose, or I don't even write if, so A is equal to PDP transpose, what does that tell me about A transpose? Well, A transpose is equal to PDP transpose transpose. And now if you remember how transpose interacts with matrix multiplication, you reverse the order. So this is P transpose transpose, D transpose, P transpose. Sorry, this is equal, this is not implies, right? But now what's P transpose transpose? That's just P. What's D transpose? Remember, D is diagonal. So that's just D. And P transpose is just P. So this is A. So this is the one-line proof of this fact. So orthogonally diagonalizable implies that the matrix is symmetric, right? So this condition means symmetric. So any questions about this statement? This is sort of not a deep statement. Okay, so if this happens, then this happens. And now I'm going to write a statement that's much less obvious. So this is a theorem called the Spectral Theorem. And I would say hands down, this is my favorite theorem in all of math. It's definitely one of the most important theorems in all of math. And it's also my favorite. So here's what it says. If it says that the converse is also true. So it says if A is symmetric, if A is real and symmetric, then, okay, two things happen. All the eigenvalues of A are real. And the second thing is it's orthogonally diagonalizable. Okay, so A is orthogonally diagonalizable. Okay, so in equations, the first statement is that AVI equals lambda I VI for real lambda I. So as in, okay, if this is true, then lambda I is real. So or I'll just write in R. So all the eigenvalues are real. So you don't have to worry about complex eigenvalues. And the second statement is saying actually A is equal to PDP transpose, where D is a diagonal matrix containing these real eigenvalues, and these V1 through Vn are an orthonormal basis of Rn. Okay, so that's called the spectral theorem. And it's kind of great, right? Because remember, before the midterm, we were going through a lot of trouble to check whether matrices are diagonalizable, right? You had to find all the eigenvalues, you had to check the eigenspaces, you had to check their dimensions. In this case, all you have to check is it's symmetric, and that's easy, right? You just eyeball the matrix and you see if it's symmetric. And you get these very nice consequences out of it, that the eigenvalues are real. And it's not only is it diagonalizable, it's orthogonally diagonalizable, which is even better. So that's the statement of the spectral theorem. We won't prove this. It's a bit, not that hard to prove, but it's a little bit, it's harder than the other theorems we've looked at. We won't prove it, but that's the statement of the theorem. So along with the easy fact that says a matrix is orthogonally diagonalizable, a real matrix, if and only if it is symmetric. So any questions about this statement?
So, Professor, can a matrix that's not symmetric still be diagonalizable, right?
It can be diagonalizable, but not orthogonally diagonalizable.
Yeah, yeah.
Right. So together, these two statements are saying that orthogonally diagonalizable is the same as symmetric, right?
Yeah.
Yeah. So this is the converse to the easy fact. And okay, I mean, everywhere the matrices are real. If A real, yeah. Any other questions about this?
Someone asked, where does the name spectral come in?
Spectral comes in because eigenvalues are generally referred to as, the set of eigenvalues is called the spectrum. And this originally comes from physics. So, you know, in physics, there's like a spectrum of light, or if you look at atoms and you look at the, whatever, you shine light on them and look at what comes out, you get these lines, which are also called spectral lines. All of those things are actually eigenvalues of something. So if you study quantum mechanics, you learn that. And so really the spectra that we see in real life in physics actually correspond to eigenvalues. So spectral is just a general word for anything related to eigenvalues. usually of symmetric matrices. Any other question? Okay, so that's just a statement of the theorem. Now, I won't prove the theorem, but I'll prove a small part of it. Namely, I'll prove that whenever, whenever you have two eigenvectors of a real symmetric matrix with different eigenvalues, then they must be orthogonal. So that doesn't prove item 2 because it doesn't tell me I have n of them and orthogonal ones. It just tells me if I have two eigenvalue vectors with different eigenvalues, they must be orthogonal. So I'll prove a part of the theorem, and you'll see how symmetry plays a role. So proof. So here's a sort of weaker statement. If A is real and A equals A transpose, and A V equals lambda V, let's say W equals mu W for V and W eigenvectors, and lambda and mu eigenvalues are distinct. So you have different eigenvalues. So earlier we saw that this means that the eigenvectors have to be linearly independent. Well, now I'm going to show you then they have to be orthogonal. Then V dot W equals 0. Okay. So we'll prove this little statement and you'll see where symmetry comes in. So what's the proof? Okay. Well, the key is to look at this quantity, W transpose AV, in two different ways. So the first way is we're going to group the AV together. I can do that, right? But what do I know about AV? So what do I know about AV?
It's equal to lambda V?
Yeah, it's equal to lambda V. It's an eigenvector. So this is equal to W transpose lambda V because of the first equation here, right? By star. Okay, so then this is equal to lambda times W transpose V, right? Okay, now I'm going to write this another way. I can also group the first two terms, right? This is W transpose A times V, right? And now I'm going to use that this is equal to A transpose W, the whole thing transpose, times V. That's just because of AB, the whole transpose is B transpose A transpose. And now I'm going to use the key property of symmetry to say that, well, this is actually equal to A times W transpose V. So I use symmetry there. This is the key step. And AW is just mu times W transpose V, right? So here's where I use symmetry. So it's a sneaky computation, right? I just group the terms differently. And I can either push the A onto the W eigenvector or onto the V eigenvector. But now these two things have to be equal, right? These two must be equal. So what does that mean? Well, it means mu minus lambda times W transpose V equals 0, right? Because I just rearrange. But this is not 0, right? Because I assumed these eigenvalues are distinct. Any questions so far?
Why is mu not being transposed in the left blue circle?
It is being transposed. Good question. Mu is being transposed, but mu is a number.
Oh,
right?
that's right. That's right.
Mu
It's just
transpose equals mu. Mu is just a number.
okay. Thank you.
Good question. Yeah. Okay. But now I'm almost done because, you know, if this is 0 and the first factor is not 0, then W transpose V has to be 0. So I just proved that any eigenvectors coming from distinct eigenvalues of a symmetric matrix must be orthogonal. Okay. So that's the proof of sort of a weaker statement, which shows how symmetry implies orthogonality. The hard part of the theorem is proving that there are actually n of these eigenvectors. And so you have enough to make it diagonalizable, but we won't do that part. So any questions about this little proof here?
Could you say the last sentence you said, like summing up the proof, because I need to like hear it in words.
Well, summing up the proof, I mean,
sorry, what you.
Oh, you mean the difference between what we proved and what's here?
Yeah.
Yeah. So the difference is that here, this means that this implies that there are n linearly independent eigenvectors, right? Actually orthogonal, right? Right? But what we proved is not, we never proved that there are actually n eigenvectors. We just proved if you have two eigenvectors from different eigenspaces, then they're orthogonal. So that's what's missing from the full statement. Does that make sense?
Yeah.
Yep. Okay, so that's the statement of the spectral theorem. Now, what's the, you know, maybe, well, or you know what? Let me actually show you an example. So, for example, let's just look at our matrix that we had earlier in the lecture, right? That's symmetric. So the spectral theorem tells me that the eigenvectors of this must be actually orthogonal. So let's just check that. So let's find the eigenvalues. So step one, you know, characteristic equation is determinant of, I guess, 1 minus t minus 1 minus 1, 1 minus t, which I calculated it earlier, is t squared minus 2t. So this implies that the two eigenvalues, so this is just t times t minus 2. So the eigenvalues are lambda 1 equals 2 and lambda 2 equals 0 eigenvalues. And then, okay, now I'm going to find the eigenvectors. So the eigenspace is E lambda 1. This is the null space of A minus 2i, which I'll do row reduction, which I again did at home. And you get that this is the span of this vector, 1 over square root 2 minus 1 over square root 2. And the reason I wrote it this way is because I want this to be a unit vector. And the reason I'm writing it that way is because the theorem says, so ONB, okay, maybe I should, orthonormal basis, I'm going to write in a short form as ONB. And so the spectral theorem says that there's an orthonormal basis of eigenvectors. So to see that, I'm just going to normalize all the eigenvectors that I find, right, by scaling them to be unit vectors. And that's why I have a unit vector here. So let's call this vector V1. And then, okay, the other eigenspace, the null space of A minus 0 identity. If you do row reduction, you get that this is the span of 1 over root 2, 1 over root 2. Again, it's a unit vector. Let's call this V2. And if the theorem is correct, these better be orthogonal. So let's just check this. So indeed, V1 dot V2 is a half minus a half, which is 0. Okay, so we verified the theorem on this example. And so, you know, in yeah, and you know, now we have the eigenvectors, we can form a matrix, you know, to actually write it as PDP transpose here, if we want. So we computed the eigenvalues and eigenvectors. So now we can put them in a matrix. We get 1 over square root 2 minus 1 over square root 2, 1 over square root 2, 1 over square root 2. D contains the eigenvalues. Then A equals PDP transpose. So by the way, does anybody recognize this matrix here? So can anybody tell me, you know, what this matrix does? Can you describe it in words?
Rotation by negative pi over 4.
Yeah, rotation by negative pi over 4, right? Because, right, cosine negative pi over 4 is 1 over root 2, and sine negative pi over 4 is minus 1 over root 2. So this matrix is actually rotation by negative pi over 4. Okay. So what does that say about P transpose? I mean, you can write it down, but P transpose is just P inverse, right? So can you think of what that is conceptually in this example?
Go the other direction.
Other
Rotates the
direction,
other-
so rotation by pi over 4. So these rotation counterclockwise, right? In math, the convention is to be counterclockwise. So this is rotation counterclockwise. And so what is this factorization now saying? Right, okay, so I mean, yeah, so I've written A as PDP transpose, right? Now P transpose is rotation by pi over 4 counterclockwise. D is just a scaling of the coordinates, and A is a rotation clockwise by pi over 4, right? Because it's a counterclockwise by minus pi over 4. And so what this is saying is that if you look at what A does, so maybe I should call this section, you know, interpretation. If you look at what A does, well, so, you know, if you start off with R2, I mean, okay, maybe I should make some more space for this because I don't want to get crowded. Let's see here. Yeah, I'm just going to move everything up a little bit. Okay, I guess this didn't work out. Okay, fine. So that's fine. So A is equal to PDP transpose. And let me just draw what this does to R2, right? So here I have a copy of R2. And you know, I'm drawing the standard basis vectors. And you know, just for illustration, I'm going to draw a circle around them. Okay. So when you apply A to these vectors and to this circle, so first you apply P transpose. And what happens now? Well, it just rotates this picture, right? So now you're in this new copy of R2. But you've rotated everything counterclockwise by minus pi over 4, which means clockwise by pi over 4. So now you're in the situation, sorry, these should be the same length. And then there's this green circle that has it changed. So this is just rotation by pi over 4 clockwise. Then you hit it with with D, sorry. And now what happens, I'm just trying to visualize by plotting these vectors in this point. What happens here? Well, what you're doing is you're stretching the x-axis by 2 and flattening the y-axis, right? So actually in this case, both of these vectors collapse into a vector that's twice as long. They get flattened. And this circle also gets collapsed into like a degenerate, it's actually a one-dimensional thing. Okay, so the meaning of this D step is to scale the coordinates. By 2 and 0 respectively. And then when you apply P again, it's just going to rotate it back, right? Rotate by pi over 4 counterclockwise. So when I plot it, my vectors are going to look like this. And of course, I mean, this green thing is just supposed to be really degenerate, right? So that's how you interpret this factorization. It's rotate, scale, rotate back. So orthogonal diagonalization has a very clear interpretation. So let me write in general. So in general, because orthogonal matrices are like high dimensional rotations. So in general, PD P transpose means rotate, scale axes, rotate back. So I'm gonna. This is interpretation 1 of the spectral theorem. And this is kind of amazing, right? So it says every symmetric matrix can be written this way. And in general, of course, geometrically, what's going on here is that the lengths of these axes in this ellipse are the eigenvalues, right? So, I mean, in this case, it's degenerate, but in this case, this little degenerate ellipse has principal axes that are of length 2 and 0. And those are the eigenvalues. So symmetric matrices map circles into ellipses, and the lengths of the axes of the ellipses are the eigenvalues. That's the meaning of the spectral theorem, at least interpretation 1. So that's interpretation 1 of the spectral theorem. Any questions so far? Okay.
So the 2 unit vectors there, or sorry, the 2 standard basis vectors that you started off with end up at the same place?
They end up at the same place, yeah. Actually, wait a second. Did I do something wrong? Whoops, I swapped P and, so they don't end up at the same place. Sorry, they don't end up in the same place. I switched P and P transpose. I'm so sorry. So this picture is actually wrong. So let me fix it. They don't, right? Because you can just check. AE1 is something and AE2 is negative of that thing. So actually this picture, so yeah, I messed up the signs. I'm glad you caught that. So right, P is R minus 4. And the first thing I'm doing is P transpose. So I actually messed up the sign. So I rotate the other way first in this case. Sorry, not capital R. So and then here I get a minus 4. Okay, so let me fix these pictures. So I messed up the rotation. So I have to now actually rotate it the other way. Right. And now when I scale the coordinates, I don't get two copies of I don't get the same vector. I get two vectors that look like this. They do get flattened, but they don't get flattened to the same thing. And now when I scale it back, I get something that looks like this. Okay, yeah. So I messed up a sign, but you're right. And so you don't get the same vector, but you do get a vector and it's negative, which is consistent with what you get if you just multiply the matrix by E1 and E2. Thank you. I'm glad you got that. Any questions?
Professor?
Yep.
So when you said that the components, like the length of the vector, are the eigenvalues, does it only work when we start with a unit vector?
Right. So yeah. So in this picture, yes, that is only for a unit vector because this green thing is a unit circle. And the reason the lengths are 2 and 0 is that you multiply 1 by 2 and 1 by 0. If you started with some other length vector, then they would also get multiplied by 2 and 0, but they would just get scaled by that. That wouldn't exactly be the axis. So the summary of it is A of the unit sphere has principal axes, is an ellipse with principal axes whose lengths are the absolute values of the eigenvalues. Is an ellipsoid, if you know what that is, it's a higher dimensional, whose principal axes have lengths, absolute values of the eigenvalues. So this is the geometric interpretation. Yep.
Going back to the previous example, the final line, I was just thinking, shouldn't it look more like a negative x? Some people say.
Yeah, I think we rotated by
I rotated
pi over 4 twice.
Thank you. Yeah, I have to change the direction of rotation. Okay, yeah, I rotated the wrong direction. Thank you. Yeah. So because you rotated by pi over 4 counterclockwise, yeah, you get this. Thank you. Thank you. Yeah. Right. So in the first picture, I didn't have to change the circle because if you rotate a circle, you just get a circle. The second picture, second rotation, it did matter because if you rotate an ellipse, you don't get the same thing back. So that's the first interpretation of the spectral theorem. And how to calculate is easy. So general algorithm to calculate, to orthogonally diagonalize symmetric matrix A. Well, just diagonalize it, right? So solve the characteristic equation And you know this will have all real solutions by the spectral theorem. And then, you know, find bases for the eigenspaces. Just as before, this is just row reduction. And the only new step is, you know, if you have multiplicity, so if you have distinct eigenvalues, they're going to be orthogonal for free, right? But if you have multiplicity, you're going to need to make them orthogonal. So use Gram-Schmidt to find an orthonormal basis of each E lambda, and then take their union. So the algorithm is basically the same, except you may have to do a little Gram-Schmidt if you have an eigenspace with a high geometric multiplicity. So this is the interpretation, and how to do this is almost the same, except you may need to, you know, if you have multiplicity, you may need to enforce the orthogonality. So any questions? Okay, so before moving on, I want to tell you a second interpretation, which is the additive interpretation of the spectral theorem. So interpretation number 2. So in interpretation number 2, suppose A is symmetric, A is equal to P, D, P transpose for some matrix of eigenvectors, which I know are an orthonormal basis of Rn and a matrix of real eigenvalues, a diagonal matrix, right? So I'm going to now interpret this in a slightly different way. So this is an orthonormal basis of Rn. So what I'm going to do is I'm going to think about what this does to a vector a little differently, right? So observe Ax is equal to P D P transpose times X. So what I'm going to do now is, you know, I'm not going to, previously I was thinking, oh, P transpose is a rotation and I'm interpreting it geometrically. Now I'm going to just look at what multiplying P transpose by X means. Well, you know, by the high school definition of matrix vector multiplication, multiplying a matrix by X just takes dot products with the rows, right? So you get V1, I'll just write it this way, V1 transpose X. These are just numbers now, all the way to Vn transpose X. And then multiplying by diagonal matrix does something kind of obvious as well. It just multiplies each coordinate by that number. So you get lambda 1 times V1 transpose X, lambda n times Vn transpose X. Any questions so far? Okay. And now using the other interpretation of matrix vector multiplication, if I multiply a matrix by a vector, I'm just taking a linear combination of the columns, right? So if I do this, I'm actually just going to get a linear combination. So I'm going to get lambda 1 times V1, I'll write it as a dot product, dot X times V1 plus lambda 2 times V2 dot X times V2 all the way up to lambda n Vn dot X times Vn. Anybody recognize this? Like, where have you seen something like this?
It's like the projection.
It's like the projection formula, except you now have lambdas in front of the terms, right? It's the same as the projection formula, except you have the lambdas in front of the terms. And so the way to think of it as a projection is this is just lambda 1 times the projection onto the span of the first eigenvector of x plus lambda 2 dot 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 all the way up to lambda n times the projection onto the span of the nth eigenvector of x. And so if you were to write that as a matrix, that would just be lambda 1 v1 v1 transpose plus lambda 2 v2 v2 transpose all the way up to lambda n vn vn transpose times x. So this is a different interpretation. What it's telling you is every symmetric matrix is just a weighted sum of projections onto the eigenvectors, and the weights are given by the eigenvalues. Okay, so I'll just summarize that in words. A is a weighted sum of projections onto the eigenvectors with weights given by the eigenvalues. Which are, by the way, real because it's a symmetric matrix. Okay, so I mean, if you do physics, maybe you've seen this. This is like the basis of almost everything in quantum mechanics. I've heard people call this the fundamental theorem of physics. I mean, if you haven't seen that yet, maybe you'll see it later. But this is a different interpretation. It's a weighted sum of projections, orthogonal projections. So that's interpretation number 2. And in our example, you know, we can just work it out. In our example, so for our example, let's just write it down. So in this example, we have that A is equal to 2 times the, so what was the first eigenvector times its transpose? So 1, so it's 1 over root 2 minus 1 over root 2, right? Plus 0 times the other eigenvector. Okay, and this might look a little funny because you're not, I mean, this is actually a 2 by 2 matrix, right? Because this is a 2 by 1 vector times a 1 by 2 vector, which is a 2 by 2 matrix. Okay. And so, yeah, this is a different interpretation of the spectral theorem. So any questions about this? So this is lambda 1, this is lambda 2.
So if you're going to be graphing things in these eigenspaces defined by eigenvectors, do you adjust lambdas?
What do you mean by graphing things?
Like if you wanted to create a sphere, what would you be using as your variable? Because x is the answer.
Wait, so I'm a little confused. So are you going back to this picture now?
No, so when we change the lambdas in an orthogonal eigenvector space, that's sort of changing the fundamental bottom line of how you're going to create something. So if you wanted to make a space in 3, if you want to make a sphere in the 3 eigenvector orthogonal eigenvectors, what is the number you're changing? Is it the lambda that you change, or does that just change the scale of how you would measure it?
I'm not sure I understand. So lambdas,
I'll write it in an email.
So lambdas are just the eigenvalues. They're fixed. You can't, you know, they're a function of the matrix. You don't change them.
You don't change them. Okay.
You don't change them. I mean, maybe what you're saying is that maybe you're wondering how this gives the same answer as this picture here.
Yeah.
Okay, yeah, okay. So let me explain that. So so what's the picture associated with this? So the picture is that I have R2 and I have two eigenvectors. So V1 looks like this and V2 looks like this, right? And what A is doing in this case, according to this formula, is it's taking whatever my X is. So let's say it's taking this X. It's taking the orthogonal projections onto these eigenspaces. Okay. And then it's multiplying the projection onto the, oh, I'm sorry. It's multiplying the projection onto the V2 eigenspace by 0 and multiplying the projection onto the V1 eigenspace by 2 because those are the eigenvalues. And so what ends up happening is you get this picture, which is the same as before, because the other component gets killed. Does that explain?
I understand. Okay, thank you.
So instead of rotation, we think of it in terms of projections. So maybe you can call this the projection interpretation. And the other one is the rotation interpretation. Both are valid. Okay, both are useful in different contexts. Does that answer the question? Yeah. So you can see now why the sphere gets flattened, right? Just the part of it in the V2 direction just gets killed. And the part in the V1 direction gets stretched by 2.
That makes sense.
Okay. So, so those are the interpretations of the spectral theorem. And we'll talk more about it later. It's very closely related to differential equations. What I want to do now is start talking about singular vectors. Okay, but let's just maybe take, I don't know, even like a 20-second break just to, in case there are any more questions.
Yeah, I was just wondering, like in the algorithm to compute orthogonally diagonalizable A, the last step, what does A divided by S mean?
Oh, sorry,
Like
Gram-Schmidt. So yeah, maybe I should just write this.
Okay.
So yeah,
okay.
so use Gram-Schmidt.
Gotcha. Thank you.
Yeah. So we didn't have to do it in this case because the eigenspace had dimension 1. But if it had higher dimension, you would have to do that. Okay, so I mean, I should say, like, in many areas of math, all the matrices you'll ever encounter are symmetric. So this is simple and useful. I mean, I personally never actually encountered a non-symmetric matrix until like 5 years ago. So, yeah. Okay, so let me now move on to the second topic, which is singular vectors. So now we switch to rectangular matrices. So this is section 7.4. So we switch to rectangular matrices. So suppose A, M by N, real, could be a rectangular matrix. Now what we're gonna do is we're gonna do something interesting with this rectangular matrix by looking at an associated square matrix. So key observation number 1 is that doesn't matter what A is, A transpose A is always symmetric. Let's check that, right? Take A transpose. Well, by the rule for transpose of a product, that's A transpose times A times A. Sorry, that's A times A transpose. That's A transpose times A transpose, which is just A transpose A. So this is symmetric. What are the dimensions of this matrix, by the way? A transpose A?
N.
N by N, right? So this is an N by N matrix. So that's kind of interesting, right? You start with any rectangular matrix, you can form the symmetric matrix. And that means you can apply the spectral theorem, right? So by the spectral theorem, there is an orthonormal basis, let's say V1 through Vn of Rn, such that A transpose A V1 equals lambda 1 V1 all the way up to A transpose A Vn equals lambda n Vn. And all these are real, right? By the spectral theorem. So I'm looking at the eigenvectors of A transpose A, which is square and symmetric. Okay. So now the second key observation is that the eigenvalues are non-negative. They're not only are they real, they're non-negative. So let's check that. Well, so I'll write it down. All the eigenvalues are non-negative. So what's the proof? Well, if you have an eigenvector, sorry, not A transpose A, Vi equals lambda I Vi. Or I won't write if, I'll just use arrows. Well, this implies I can do a sneaky thing now. I can multiply both sides by Vi transpose. Okay, anybody know how to simplify, well, the left-hand side? Or how about the right-hand side, actually, for now?
Dot product.
Yeah, so Vi, what's Vi transpose Vi?
Vi dot
Vi.
Vi.
Okay, and what is it? So, you know, we chose Vi.
Squared.
It's norm of Vi squared, which is?
1.
1, because it's an orthonormal basis, right? And so this is 1. And what about the left-hand side? So I'm going to do a sneaky trick. I'm going to write that as AVI, the whole transpose times AVI. I can do that. Equals lambda I, right? But now the left-hand side, you know what happens when you take a vector and you take a dot product with itself?
It's the length.
It's the length squared. So this implies lambda I equals norm of A Vi squared, which is non-zero. So that's the proof of key observation 2. It's a sneaky little trick that the special form of this matrix, that it's a type of matrix that can be written as A transpose A, implies that all the eigenvalues have to be non-negative. They could be 0, but they can't be negative. So any questions about key observation number 2? Okay. So now, so you can reorder the eigenvalues So that lambda 1 is the biggest one, lambda 2 is the second biggest one, lambda n is the smallest one. And let's suppose exactly r of them are non-zero. Okay, so let's suppose exactly r are non-zero. So maybe I'll write it a little more explicitly. So lambda 1 r plus 1 equals lambda r plus 2 equals all the way up to lambda n equals 0. Okay, so there are non-zero eigenvalues. And okay, since these numbers are non-negative, I can take their square root. Okay. So here's the definition. Sigma 1 equals square root lambda 1. Sigma 2 equals square root lambda 2. All the way up to sigma r equals square root lambda r are called the singular values. Well, or okay, I mean, you can define them all the way up to lambda n, actually. So there are n of them, and the first r are non-zero. And by this little key observation number 2, I actually know what they are, right? I know that that these satisfy that the I singular value is just the norm of A times Vi. Okay, so I haven't done anything. I've just collected some information so far. The relevant information is there's an orthonormal basis V1 through Vn of Rn. The eigenvalues are non-negative. And then I've looked at the non-zero ones, and I've defined these, these numbers that are the norm of A times Vi. Okay, so now I'm going to do something that's interesting with these vectors and with these numbers. So I'm going to state a theorem now. But any questions about the setup so far?
Yeah, I think I missed it exactly. But what are we defining for R? Like,
oh yeah, sorry. R is the number of non-zero eigenvalues.
Oh, okay.
Okay, so now I'm going to prove a theorem saying that this tells us a lot about the matrix. So here's a statement of a theorem. So suppose A, which is m by n, has singular values sigma 1 through sigma r, which are non-zero, and then the rest equal to 0. And suppose A transpose A has eigenvectors v1 through vn as above. Okay. Then the following three things happen. First is the rank of A is equal to R. So the rank is equal to the number of non-zero singular values. Okay. Second property is if you look at the corresponding eigenvectors of A transpose A, this is an orthonormal basis of the row space of the matrix. So if you look at the eigenvalues of A transpose A corresponding to the non-zero singular values, they give you an orthonormal basis of the row space. And finally, if you look at the images of these things, this is an orthonormal basis of the column space. Okay, so this gives you a bunch of good stuff all at once, right? It tells you the rank, gives you an orthonormal basis of the row space, and it gives you an orthogonal basis of the column space. So let me draw a picture illustrating this. So there's a picture, and I hope you watched lecture 20 where I proved the fundamental theorem of linear algebra. The picture is, so you have A that's going from Rn to Rm, and Rn is decomposed into two orthogonal subspaces, namely the row space of A and the null space of A, which are orthogonal complement. And what we proved in the previous lecture is that there are two orthogonal subspaces of Rm, namely the column space of A, and I guess this would be the null space of A transpose, which is the column space of A perp. And what's going on is that A is an isomorphism, or multiplication by A is an isomorphism between the row space and the column space. Okay. So this was the fundamental theorem of linear algebra that I proved, well, that you saw a video of me proving earlier in the previous lecture. And what this theorem is telling us is more, right? So previously okay, just to remind you, TA of x is just AX. And TA goes from the row space. Or I guess we use TA for something else. Let's call it T. So T of x is this. T goes from the row space of A to the column space of A. Okay. And what this new theorem is telling us is that there's a pair of orthonormal bases that get mapped to each other. So let me move this picture away since okay. So there's a special orthonormal basis sitting, or maybe I'll draw it. Yeah, there's a special orthonormal basis sitting over here, because consisting of V1, V2, V3. And that gets mapped. So in general, if you have an isomorphism, a basis gets mapped to a basis, right? But that doesn't, in general, an orthonormal basis doesn't get mapped to an orthonormal basis by an isomorphism. There's nothing in there that says it has to preserve orthogonality. But the special thing about this basis is it gets mapped to, maybe I'll write it in a different color. It gets mapped to an orthogonal basis of the column space. Okay, so maybe I'll give these names. So let's call this, well, I'll give them names later. So that's what the theorem is saying. That the dimensions are the ranks, and there's a special orthogonal basis of the orthonormal basis of the row space that gets mapped to an orthogonal basis of the column space. So any questions about the statement? The proof is actually not hard. I'll do the proof on the next page. Any questions? Okay, somebody asked, was there important stuff in lecture 20? Yeah, lecture 20 was really important. So, you can watch it afterwards. Okay, so let me give you a proof of this. Okay, so I'm going to actually prove these statements in reverse order. Okay. So I'm going to start with item 3. Well, the column space of A is the set of AX so that X is in Rn. That's the definition. But since V1 through Vn here is a orthonormal basis of Rn, this implies this is just the span of AV1, AV2, all the way to AVR, AVR plus 1, AVN. Okay. Now, what do we know about VI? Well, these are well, okay. I mean, sorry. Let's see. Okay, sorry. Actually, I need to do this a little bit differently. Let me start with column space of A transpose A. And then the same reasoning works for A transpose A. And these are all now A transpose A. Okay, but now these V1 through VR were eigenvectors of A transpose A, right? And remember, the eigenvalues lambda 1 through lambda r are not 0, and the rest are 0, right? So what that implies is that actually all of these terms are just 0 because the eigenvalues after the rth one are 0. So let me write that here. And so then this is just the span of the first r of them. Oh, I'm sorry. Okay, I really messed this up. Let me do it again. What I wrote didn't even make sense. So the column space of A transpose A is not the same thing as the column space of A, right? So right, okay. So I have that the column space of A is the span of AV1 through AVR, AVR plus 1, all the way up to AVN. And now I'm just going to use that I know that AVR plus 1 through the rest of them are 0 because sigma R plus 1 through sigma N is 0, right? Using this fact over here. So I know that these are 0. Since sigma R plus 1 equals all the way up to sigma N equals 0. So this is the span of just these vectors, AV1 through AVR.
Why the column space of A equals the span of AV1? Like the question suggests that A transpose A has eigenvectors of V1 to Vn.
Right. So here I'm just using that V1 through Vn is an orthonormal basis of Rn. I'm not using the eigenvector equation. Right. This is just a fact about any basis. This is like a pre-midterm one kind of a fact that if you have a basis of Rn and you look at, then the column space of A is just 8 times the vectors, span of 8 times the vectors in that basis.
Yeah, okay.
Yep. And I'm using though that I know that AVR plus 1 through AVN are 0. I am using that because remember sigma I is equal to norm of AVI. And I specifically chose, R so that only up to sigma R is non-zero. Right? Okay, so now I know that AV1 through AVR span the column space. Now to prove that and I know they're not 0, right? These are all non-zero. Because again, I chose sigma r to be the last one that's non-zero, right? So I have a bunch of non-zero vectors spanning the column space. Now I need to show that they're orthogonal, then I'll be done, right? Because that's what an orthogonal basis is. So now the key observation is if I take a dot product between two of these things, so for I not equal to j, both less than r, well, this is vi transpose A transpose A vj. And now I use the eigenvector equation. So what if I use the eigenvector equation, what do I get?
It's the length. It's similar to the other slide.
Yeah, so I'm using that these are eigenvectors of A transpose A. So, you know, they become scalars, Vi transpose lambda j Vj by the eigenvector, right? But now this is just lambda j times Vi transpose Vj, which is 0 because remember, they're orthogonal, right? So therefore, AV1 through AVR are orthogonal. So they span and they're orthogonal, therefore they're an orthogonal basis. So that's the proof of the third item. And that's the hardest part. Once you get that, the other ones kind of come for free. I'll do it in a moment. But any questions about that? Okay, so we proved item 3. And now I need to, so I have an orthogonal basis of the column space. How do I get that V1 through VR is an orthonormal basis of the row space? So by the way, this immediately implies item 2. Why does this imply that the rank is R?
Because if it's a basis with R elements, then the dimension of its column space has to be equal to that number.
Exactly. The rank of A is the dimension of the column space of A is equal to R because I just produced a basis with R elements in it, right? In fact, I produced an orthogonal basis, but it's also a basis. So 2 is also fine. Oh, sorry, a 1 is also fine. So this is item 1. Should be. And now the last thing I need to prove is that V1 through VR is an orthonormal basis of the row space. So I need to show span of V1 through VR is the row space. I already know they're orthogonal, right? By the spectral theorem. So I need to show they span the row space. Why is that? Look at this picture and think about it.
Because it's an n by n and it's isomorphism?
Close. It's not because it's n by n, but it is because it's an isomorphism, right? So we proved that this here is an orthonormal basis, right? And an isomorphism maps a basis to a basis. That's a sort of midterm 1 kind of a fact, right? So now if you apply the inverse, you should get a basis of the, basis of the row space, right? And that's what we do. So observe. So AV1 to AVR is a basis of column space of A, implies that the T inverse of AV1, T inverse of AVR is a basis of the row space of A. because of the isomorphism property. But that's just V1 through VR. Okay. So that proves the third and final property. So okay, these are called the singular values. And I guess I'm out of time, but I might as well just finish with the terminology that these vectors are called the singular vectors. So terminology. V1 through VR are the left singular vectors. Sorry, are the right singular vectors. And then if you look at AV1 and you normalize them, or VR, I guess. Are the left singular vectors. And this is an orthonormal basis of the row space. This is an orthonormal basis of the column space. And the key relation between them is that A times Vi equals sigma I times Ui. That's just by definition, since sigma I is just equal to norm of A Vi. So this is like the eigenvector equation, except it maps the right singular vectors to the left singular vectors. So anyway, we're going to talk a lot more about this next time. But that's it for today. Sorry to go over time. But any questions?
What's the character after sigma?
UI.
That looks like a U.
UI, yeah. This is a UI, so I can write it more clearly. Is that better?
Yeah, thank you.
Oh yeah, sorry, I didn't. These are U1 through UR. Let's call these U1 through UR, yeah. I'll emphasize that it's a U.
Thank you, that was fascinating.
Yeah, thanks for asking so many questions. I'm sorry I didn't get to do concrete examples. The proof took longer, but I'll do some next time. And yeah.
Professor, I have a question about the part where you said we want to reorder our eigenvalues so that it's in decreasing order.
Yeah.
Why would we want to consider that many zero eigenvalues to start with?
Oh, I mean, we're just defining R to be the last non-zero eigenvalue. So it could be that there are no zero eigenvalues. Right? So the number of non-zero eigenvalues is equal to the rank. That's what this theorem says, right?
Mm-hmm.
So I'm just saying that we can, the eigenvalues don't come with names. It's just going to be convenient to sort them. So all the non-zero ones come first, and then the zero ones are later, because then it'll just be easy notationally.
Because like if they're all zero, why would we still call them, like, I guess, different eigenvalues?
Right. I see what you're saying. I see what you're saying. So the way we're thinking about it here is if an eigenvalue has a multiplicity, then we're just going to write it down twice.
I see. Okay. Thank you.
Because we have these n eigenvectors, right? So we do need to associate for each eigenvector and eigenvalue.
So it could be possible that the eigenvector associated with, I guess, the different zero eigenvalues are different?
Yeah. The eigenvectors will be different because remember, we've chosen an orthonormal basis of eigenvectors.
Okay.
So I mean, if you follow what we did in part 1 about how to compute these, that's going to come from this Gram-Schmidt in step 3, right? That if there's a zero eigenspace and there are a bunch of eigenvectors, you're going to get a bunch of orthogonal eigenvectors from Gram-Schmidt.
Okay, I see. Yep. Thank you.
Any other question?
Will we have homework due on Tuesday consisting of section 7.1, 7.4 since we didn't get to SVD?
No, I'm going to move section 7.4 to the next lecture. But you will have
Okay.
7.1.
7.1 will be due on Tuesday then?
Correct.
Okay, thank you.
Can you go back to the last line you had in the slides?
Sure. This one or this one?
Yeah, right here.
Professor, I have one question, but I'll
Sure.
probably wait. I didn't quite understand the weaker statement we made at the beginning.
Oh, you mean this?
Yeah, the point. Yeah, the point of the proof.
Oh, you don't understand the proof or the statement?
Both.
Okay. So
Like
the
I
point...
understood the proof. I understood the proof, but I didn't understand the point of the statement.
Oh, so the point of the statement is, so remember, if you have any matrix and you have two eigenvectors that come from different eigenvalues, then they have to be linearly independent, right?
Yeah.
Here we're proving something stronger. We're saying if you have a symmetric matrix and you have two eigenvectors that come from different eigenvalues, they have to be orthogonal, not just linearly independent.
Oh, okay.
So this is stronger.
So we're saying the the eigenvalues are orthogonal?
No, the eigenvectors are orthogonal, assuming the eigenvalues are distinct.
Okay.
Yep.
Makes sense. Thank you so much.
Sure.